Now the question is, what happens when a particle combines with its antiparticle? And, uh, and we understand when a particle combines with its antiparticle, uh, its mass converts into energy using Einstein's mass-energy relationship. Let's have some detailed analysis of it, a little bit of detailed analysis of it. And what happens is that when a particle combines with its antiparticle, now if I have a particle, say, I have a particle, let us assume that I have a particle and its antiparticle as, as electron and positron. Okay, when the two combine, what they give birth to the radiation, they give birth to the photons, and this phenomenon is called as annihilation. We call this thing as annihilation. And what happens is that it results in the production of equivalent amount of energy in accordance with E is equal to mc square, Einstein's mass-energy relationship. Now, the energy that's liberated in the form of two or more photons. So how does the process take place? So what we have is, say for example, we have a particle and we have its antiparticle. Okay, what happened is they combine, and when they combine, what they come up with is 2 times m naught c square plus k positive plus k negative. Now this m naught refers to the rest mass of these two particles. So m naught is the rest mass of electron, m naught is the rest mass of this positron. So coding it like this. And what happens is that we have k plus. This is the initial kinetic energy of the particle, which was positron, and k minus is the initial kinetic energy of the particle, which was negatively charged. So what happens is that this thing results into h nu 1 plus h nu 2. So what we have is this m naught is the mass of the particle as well as the mass of its antiparticle, right? And this k plus and k minus, they are basically the initial kinetic energies, respectively. They are initial and final initial kinetic energies, respectively for the photon nu 1 and the photon nu 2. And these photons that are produced as nu 1 and nu 2, the frequencies of the two photons that have been liberated in the process are nu 1 and nu 2. Now, in particle-antiparticle situation, what we have, we call it annihilation. So it's the combining of the two particles. And what is important factor here is that the total linear momentum is also conserved. So total linear momentum is also conserved. So if total linear momentum is conserved, so how is it conserved? It is conserved in accordance with m naught, say v plus plus m naught v minus. That is equal to h cross k1 plus h cross k2. Well, this k1 and k2, they are the propagation vectors. And what is h cross? It's a modified Planck's constant, and it is h by 2 pi. So h cross is h by 2 pi. Okay, so what is important here is that this linear momentum of this reaction should remain conserved. And this v plus and v minus, they are basically the velocity vectors of the particles and antiparticles. So v plus refers to the velocity vector of the particle, and v minus refers to the velocity vector of of the antiparticle. And similarly, these Ks that we have, K1 and K2, they are the propagation constants or propagation vectors of the two photons that are formed during the reaction. So what we see here is that this is an important condition for this reaction to occur, that we must have conservation of linear momentum. And now what we have is, if we take an example of particle and antiparticle situation in case of electron and positron. And what happens here is that we have the release of two gamma ray photons. And the energy of each gamma ray photon is nearly 0.511 mega electron volts. Now, when both the electron and positron are initially at rest, so that's the point, and so to say that this is the energy. What am I writing here? This is the energy of this gamma ray photon. Now, the similar situations are true for proton and antiproton. So both at rest. So when a proton combines with an antiproton, they give rise to two photons, and these photons have. So if I have a proton positive plus proton negative, what we get is two photons. The wavelength of this photon is 6.61 times 10 to the power of minus 6 angstrom. And from here we can calculate the energy of this photon. In fact, whenever any particle and its antiparticle combine, the total mass is annihilated. It goes off, and at least a pair of photons, is produced. In view of conservation of linear momentum, the elementary particles, there happen to have the elementary particles which are acting as their own antiparticles. And the examples of those elementary particles are, they are the particle themselves, and they can act as antiparticles themselves. The very first one is the graviton. Graviton is the particle and antiparticle of itself. The next one is photon. Photon is a particle and antiparticle of itself. Say gamma ray photon. So pion, a neutral pion. Neutral pion is an example of a particle and antiparticle. And neutral mesons, they are the particle and antiparticles of themselves.